Hello students, today we are going to discuss about the mossbauer spectroscopy. So mossbauer spectroscopy is also known as gamma ray spectroscopy, so which was invented by Mossbauer, and he also got the Nobel Prize in 1961 for this invention called mossbauer spectroscopy. So the name itself indicates the spectroscopy will be observed in gamma ray region. So what is the gamma ray region? So in the electromagnetic spectrum, so the last region is the gamma ray region. So what is the main principle of this gamma ray spectroscopy? So or mossbauer spectroscopy. So 57 cobalt atom by the radioactive decay. So this is a radioactive element. The radioactive decay or by the electron capture, by absorbing the electron, this cobalt atom will be decayed into iron 57 in the excited state. 57 cobalt atom by the electron capture, it decayed into 57 iron atom in excited state. The half-life period of this 57 iron nucleus in excited state is around 270 days. That means 57 iron nucleus the lifetime is around 270 days. So iron 57 excited state will be de-excited to 57 iron ground state. So this is the total processor. 57 cobalt by the electron capture decays into 57 iron nucleus in the excited state. It will stay in that excited state for 270 days and it will decay to 57 iron nucleus in the ground state with a half-life period of 1.5 into 10 power minus 7 seconds. So this is the total decay procedure of 57 cobalt atom into 57 iron nucleus. The energy gap between the ground state and the excited state for this nucleus is, for the iron nucleus is 2.3 into 10 power minus 15 joules. The energy gap between the first excited state of iron nucleus and the 57 iron nucleus in the ground state is 2.3 into 10 power minus 15. So again I am indicating this total procedure by the energy level diagram. So 57 cobalt is excited by the radioactive decay. It will be converted into 57 iron nucleus in the excited state with a half-life period of 270 days. Again, this 57 iron nucleus will be decayed or de-excited to 57 iron ground state with an energy gap 2.3 into 10 power minus 15 joules. The half-life period is 1.5 into 10 power minus 15 seconds. So here the energy gap between the first excited state and the ground state of iron nucleus is 2.3 into 10 power minus 15. Then the frequency emitted by this de-excitation can be calculated as delta E by H. So here delta E is 2.3 into 10 power minus 15 joules divided by Planck's constant is 6.625 into 10 power minus 34. So this is nearly 3, that is 0.3 into 10 power 19, that is 3 into 10 power 18. So this is a frequency, the units are Hz. Means by the de-excitation of iron nucleus from the first excited state to ground state will emit gamma rays. So this is the frequency of gamma ray. So from the 57 cobalt atom by the radioactive decay, 57 iron nucleus in the excited. The star mark indicates the excited state is formed. So from this, by the excitation, gamma rays of frequency 3 into 10 power 18 hertz are emitted. That is, from this excitation, gamma rays are emitted. So when these gamma rays are emitted from this de-excitation, if there is any 57 iron nucleus in the ground state, these gamma rays are absorbed by this iron nucleus and it is excited to 57 iron excited state. So whenever the gamma rays are emitted, these gamma rays are reabsorbed by the nearest iron nucleus. So this reabsorption of gamma rays is known as mossbauer spectroscopy. The principle of mossbauer spectroscopy is 57 cobalt atom will generate the gamma rays. These gamma rays are reabsorbed by the nearest iron nucleus. So how these gamma rays are absorbed? So in NMR or ESR, externally we are applying the external magnetic field. So using some mediator, we can able to absorb this gamma rays by this iron nucleus. So here the procedure is, these gamma rays are absorbed by, let us suppose that this iron nucleus is the absorber and this is the source. So if you moving the source towards this fixed observer, this source is moving towards and away from this observer, then these gamma rays are absorbed when the source is moving towards the observer. So this phenomenon we already studied, Doppler shift or Doppler effect. So what is the Doppler effect? Observer sees a Doppler shift by seeing the moving source. So that means the same phenomenon is observed in mossbauer spectroscopy. So the gamma ray reabsorption is gamma ray spectroscopy. This gamma ray reabsorption takes place by moving the source with respect to observer. So then there is some Doppler shift. So that is delta nu. So this delta nu Doppler shift can be calculated as, so we have the source, that is 57 cobalt, from this gamma rays are emitting. So we have the observer. So this source is moving towards and away from this observer. So this phenomenon is Doppler effect. So we can calculate the Doppler shift as mu frequency and v is the velocity of this moving source divided by velocity of light. So we already calculated the nu value as 3 into 10 power 8. So in gamma ray spectroscopy, the velocity of the source, that is 10 square meter per second. So we can move per second with 100 meters per second velocity. So by substituting these values, the frequency emitted from gamma radiation is 3 into 10 power 18 and velocity of this moving source is around 10 square meter per second and velocity of light is 3 into 10 power 8. So that is 10 into 10 square, that is 10 into 10 power 10 into 10 square, that is 10 power 12 hertz. So this is the Doppler shift of mossbauer spectroscopy. So we can define the mossbauer spectroscopy simply as the reabsorption of gamma rays emitted from the source. How these gamma rays can be absorbed? These gamma rays can be absorbed by moving the source with respect to the observer. So here is the source, here is the observer. Here we place the GM counter or scintillation counter. So for example, here 100 gamma rays are emitting Let us suppose that this observer is observed 20 gamma rays. What are the remaining gamma rays? 80 gamma rays are counted in GM counter or scintillation counter. So from this counter we can calculate what is the number of gamma rays, the number of gamma rays that are observed by the observer. So this is the main principle of mossbauer spectroscopy. So which is an important spectroscopy, and in the next class we will discuss about what are the applications of this mossbauer spectroscopy. By knowing this gamma ray spectroscopy, what we can calculate, what are the applications of mossbauer spectroscopy can be discussed later.